Hi there, my name is Søren, and I'll be presenting this paper on structural learning in stochastic processes. So what I'm about to say applies to different classes of stochastic processes, but for simplicity, I will only talk about Hawkes processes. So down here we have some data, these dots from a point process. So the data we have is essentially some streams of events. Each event is such a dot here, and for each event, I know a time point where it occurs, and I also know in which coordinate process it occurs. So in this case, we have 4 coordinate processes. And a point process is characterized by its intensities, and the intensities are themselves stochastic processes. So for each coordinate process, we have an intensity, and each intensity in each time point, it describes probability of observing an event in this coordinate process in the immediate future, conditioning on the past up until this time point. And a Hawkes process is then a point process with a particularly simple type of intensity. So for each coordinate process alpha, the intensity is essentially this linear filter. So we have a positive constant mu, a non-negative constant mu. Then we have a sum over all of the coordinate processes. So V is the index set of the coordinate processes. And then we have a sum of each. So now this is for a fixed coordinate gamma. We have a sum over all of the previous gamma events. So each of the previous gamma events may contribute to this intensity. And we should note here that the G function is not negative. And we will also assume some kind of sparsity. And we're interested in this sparsity, meaning that some of these G functions are identically 0. So essentially this structure, so down here on the left, there's a visualization of the corresponding intensities. So these are the point processes, and here there are corresponding intensities. So essentially we get a event here. The first event is in coordinate process 3, and it makes these lambda processes jump because there comes a positive contribution to this sum. Okay, so I want to make a graphical representation of this, and what we will do is to simply add a directed edge if and only if the corresponding G function is not identically 0. So this means in this case that this edge signifies that whenever there's a event in the one process, this gives a positive contribution to the intensity of the two process. And essentially I want to learn, let's say I observe data, I want to learn something about this graphical structure from data. And there are various techniques to learn these G functions, so of course I can apply them. One issue being that if I only have partial observation, meaning that some of these coordinate processes are fully unobserved, then the marginal distribution, that is the distribution over the observed processes, is not necessarily a Hawkes process anymore, and we need to do something else. Okay, so we first have to fix what is actually the graph we want to output. So I gave you a definition of a graph on the previous slide using these G functions, and this is what I would call the causal graph. So essentially, this causal graph is just given in terms of these G functions, if they're identically 0 or not. And of course, this is mostly interesting if these G functions are of interest, if we, for instance, think that this is like a physical network and these G functions are, for instance, invariant under interventions. Then it would be natural to want to learn exactly what the graphical structure is. So let's say this is now my causal graph, and we want to describe what we want our algorithm to output. And we want what we wanted to output we call the parent graph. And essentially, so this is what I have over here. Now we're in an example where the true underlying network has 6 coordinate processes, but beta, gamma, and phi are unobserved. And what we want to output is a graph which has a directed edge, for instance, from alpha to delta, if and only if there's an unobserved directed path in the true causal graph. So what do I mean by that? Well, let's see here. For instance, the red edge here corresponds to this directed path over here in the causal graph. And I call that unobserved because every non-endpoint node is marginalized away or unobserved. Okay, so this graph on the right-hand side is what we want to output. And how will we do that? Well, we will use local independence. You can think of, I will not define it, but you can think of it as being analogous to conditional independence when you're learning DAGs or marginalizations thereof. And this is what we're going to use to learn about the parent graph. Previous work has studied similar problems. We make 2 simplifications to make this computationally feasible. First of all, we only, as I already stated, we only essentially want to learn the directed part of the underlying structure. And this is what we use the parent graph for, as a formalization thereof. And we also allow a certain kind of early stopping. So we are not sure to output the parent graph itself, and the parent graph itself is also not identifiable from the local dependencies, but we are sure, under the assumption of what we call ancestral faithfulness, we're sure to, in the oracle case, output a supergraph of the parent graph, so a directed graph, and this can help us understand and describe the sparsity structure in the underlying causal graph. So thank you very much for watching.